My name is Patrick Skrodzki, and I'm a recent graduate from the University of Michigan who works under Professor Igor Yovanovich. In this poster, I'll discuss recent work in which we use filamentation to improve collection of distant optical signals. Filamentation results from the propagation of an intense ultra-short laser pulse in a nonlinear medium such as air. The filament can deliver high laser pulse intensities, though sufficient for excitation or even ablation of a target, to distances greatly exceeding the diffraction-limited Rayleigh range. Filamentation can also be combined with analytical spectroscopy methods like laser-induced breakdown spectroscopy or LIBS to enable standoff or even remote sensing. Recent work demonstrated that filamentation can be tailored to form transient waveguide structures from the propagation medium, namely air, to improve collection and transmission of optical signals. For example, the intensity or phase profile of the filament-driver can be shaped to form an annular plasma arrangement. An elevated refractive index is left in the wake of this plasma caused by a thermal gradient left in the gas, forming the equivalent of a waveguide clad, while the relaxed air in the center forms the equivalent of a waveguide core. In this work, we designed an experiment to concatenate two such filament-driven thermal waveguides on the same axis as a potential means to extend the total waveguiding distance. We separated our filament driver into two legs. Each leg was focused with a lens split into thirds to form a triangular arrangement of filament cores that later comprised the waveguide clad after the dissipation of the air plasmas. The two legs are then concatenated on the same propagation axis to form a longer merged waveguide structure. The thermal gradient persists for several hundreds of microseconds corresponding to diffusion, and here we model the evolution of the waveguide on this timescale. Next, by imaging the exit mode of a guided counterpropagating probe laser, we demonstrate that the concatenated waveguide provides better signal enhancement on the appropriate timescale than its individual segments. Further, we demonstrate that the concatenated waveguide can also be used to redirect counterpropagating probe signal. In the images on the bottom, the spot on the right appears and decays on the 100 microsecond timescale, expected for the thermal waveguiding mechanism. And by comparing with the reference spot on the left, we see that the right spot is indeed a redirected signal, evidenced by the inverse behavior between the reference and the guided signals in time. Finally, we demonstrate that the concatenated filament-driven thermal waveguide can be used to transmit spectroscopic signals, like the emission from a laser-produced plasma. These results demonstrate that the concatenated waveguide can be used to improve the analytical performance of the LIBS technique. Here, for example, we see notable improvement in both the total signal as well as the signal to background ratios of several atomic copper lines from laser ablation of a metal target. To summarize, we demonstrated that the concatenated filament-driven thermal waveguide increases signal enhancement, enables signal redirection, and improves the analytical performance of laser-based sensing methods like LIBS. In future work, we have plans to improve the formation and arrangement of the filament cores and the waveguide segments using programmable optical devices. Please visit my poster for more information or if you have any questions, and thank you for your attention.